within Motion2, we're looking at the way it operates with continuous motion rather than point-to-point motion. So one axis following another one, that kind of thing. Some people call this web processing. So the web being some kind of thing going through a machine. It could be paper in a printing machine. It could be plastic film in a plastic film processing machine, making, I don't know, anything from carrier bags to packaging food or whatever. Not a popular thing, carrier bags these days, but in the 1990s we did do a lot of carrier bag making machines in the UK. We had 301 those, and it was quite a big industry for a while, until it suddenly became undesirable to have all this plastic around. But in fact, we also then had a second lease of life with companies repurposing plastic bag making machines to make them more high-end carrier bags, with the reusable ones, etc. So that then got us into replacing old controllers with new ones, which is quite good. So there's 4 subjects there: flying shear, doing cams, a thing called FlexLink, which when I explain that it should be reasonably obvious what it does, and registration, which is where we pick up a signal from an input and use it to synchronize one axis with another one. Now when we get into this kind of motion, we're in a different world to when we're doing point-to-point, because if it's a continually moving machine, there are no end limits. So we need to make sure we don't have software end limits set in our program. So our initialization is different. We don't have any hardware limits generally. And there's a thing called Reqtest, which is a feature on an axis that allows you to automatically count up to a value and then reset it back to 0, so that it will automatically basically go around a cycle. Now that could be 0 to 360 degrees, or it could be, if it's a length you're putting on a conveyor, it could be the length in millimeters of the product, but it will automatically reset back to 0 again. And effectively what that Reqtest does, when in the world we've been in with going from 0 to a distance and then back again, which we were doing yesterday, the Reqtest is effectively not used. It's just a number which is out there at a distance. The physical end stops on the machine would usually be less than the Reqtest, so you'd never get to the Reqtest. Yeah. And we also need, in that case, to be able to go negative, because if you imagine you move, you've datumed your axis, you know where 0 is. If you move back to 0 and the encoder, the motor goes slightly less than 0, it's got to go negative, because you've got to be able to come back to 0, back the other way again. So we have this thing on the top there where you've got basically the ability of the axis to go plus and minus the Reqtest. Why is there a Reqtest anyway? Well, there's a natural end to the travel, in that the value is held inside the controller as a 64-bit number. So if you get, that's plus and minus, so if you get 2 to the power 63 binary bits in your encoder count, you will reach the end of travel anyway. So what we've done with Reqtest is allowed you to control that, rather than just it being like 2 to the power 63, which is just a number, isn't it? We've said you can actually control where that Reqtest is, rather than just letting the logic of the processor do it for you. Obviously that means there is a limit of that. You can't go more than 2 to the power 63 binary bits of encoder. So if you get someone designing a system which is a big linear travel that's like half a kilometre long, and he's got a 23-bit encoder, just do the maths. That probably isn't going to be possible, because you'll run out of bits effectively. Okay, so anyway, when the bottom picture there is our circular motion, where we're just going around continuously in a loop on an axis forever. And what we do, we set this repeat option, rep option to 1, and then the Reqtest then goes up to the Reqtest value and back to 0. So it never goes negative. You never see a negative value. Should never see a negative value. It is possible, actually, by the way the maths works. You sometimes see a negative value, but only a glimpse as it crosses 0. But generally the idea is if you set it to 360, you get to 359, and then it goes to 0. And if you go back the other way, from 0 it will jump up to 359 again. Okay, and in the programs there is this Motion2 main routine which runs the startup again. This time we have got the wait. This is what I was talking about. A little wait there instead of the inverse, and then just wait until the proc status has got to 0. Sorry. And then we're just setting up some different speeds there, turning the S ramp off so that we're not doing any S ramping. And as I say, you need to make sure as well that any end limits have been turned off. If you've ended up with the FS limit and RS limit set inside your startup, then make sure they've been removed so that they're not set. Okay, so let's look at the very first one of these connecting or gearing commands, and it is connect. The command is connect. Some of our newer guys who've come along have been looking, how do you gear two axes together? So they search for the word gear, and they don't find it because we use the word connect rather than gear, but effectively it is gearing one axis to another. And it's really simple. You just put the ratio in and you tell it what the master axis is, what the driving axis is. The thing that isn't really simple though is that this connect ratio is in terms of encoder counts. So it doesn't use units. So if you've got your unit set for millimeters on one axis and the different units on the second axis also giving you millimeters, you've got to make sure that you do a calculation to give a connect ratio which is in encoder counts. So forget millimeters, you've got to work with encoder counts. And the reason for that is that this command was there right in the 1980s when the controllers were first sort of developed, and then processors weren't so powerful. So some of these earlier commands, they're designed to be very, very friendly to the processor, but slightly less friendly to the programmer. So you just got to do a bit of work to do the calculation yourself. If you put the value 1 in, then that's 1-to-1. If you put a value lower than 1, then you're basically gearing downwards, so the slave is going slower than the master. And if you put a connect of 2 or connect of higher than 1, then you're gearing upwards and the slave is going faster than the master. There's a slight word of warning here though, in that if you go too fast or too high a ratio, then you will run into trouble. Just before I mention that though, there's this connect 0 command which will give you no movement on the slave, so that is possible as well. You can also put negative connect, so you can go minus to make the slave go the opposite direction. That also works. Just going to check. Okay, let's just go back to that. The word of warning is that if you start gearing up too highly, you'll end up with very, very rough movement on the slave. Because this literally is, every servo cycle, the command says how many counts of encoder have occurred on the master, and I will multiply that by the ratio and apply that to the slave. So if you think of putting a connect ratio of 100 in here, that means for every one encoder count on the master, the slave will jump 100. It won't smoothly move 100 counts, it will jump 100 counts. So the higher the value you put in, the more jumpy your slave axis will be. Generally, in my experience, anything up to 5 you don't notice this effect at all. It's fine. When you get to 10 you might see a bit of nervousness in the axis. Above 10 and really you're into a territory where it's not going to perform very well. However, having said that, the assumption there is that the master and slave axes have the same number of counts. If I've got an input axis, say the encoder on these modules is 4,000 counts per turn, and my slave axis is, say, an Eston drive with a 23-bit encoder, then one count on that wheel is not the same number of degrees of angle change to my 23-bit encoder on the motor. So in that case, I could probably use quite a high ratio, and it actually would be okay, just because I have this crazily high resolution on my slave axis. So
effectively, you just sync two encoders.
Yeah, you're trying to
completely different scaling.
Yes.
Yeah.
So if they've got totally different scaling, then you could well see high counts on the high ratios on the connect. But it is a very hard lock. It is like having teeth meshed, only this time they're binary bits. They're encoder edges meshed together, and there's no smoothing or anything like that between the two. I once had a customer set something up. He phoned up and complained that he'd set his ratio to 1,000, and why wasn't it, smoothly changing the speed of the slave axis? I was explaining, well, there's nothing in there that does that. Okay, so there's a little program that's quite ridiculously simple. In fact, it doesn't really do very much. But what it does do actually is it will put a new value of ratio in every time it goes around that loop. So it's going around that loop. So the connect, it doesn't buffer up like other moves. When you put a new connect in on the same axis, it simply changes the ratio. So I've got there that I can update the ratio in VR10 as often as I want, really, and the program will just update the connect with a new ratio.
What's one application that we need to put the higher ratio for the connect? I remember there is a command called clutch rate.
Yes, well
it can ramp up.
That ramps up the ratio, but it doesn't smooth the connection.
Yeah.
The connection is still the same, but yeah, there is a connect.
It's much better.
Yeah.
So suddenly changed.
Well, exactly. So I mean, the thing about the connect as well is if you apply that to a moving master axis, it will suddenly change. Except we have this thing called clutch rate, which allows you to bring it in.
Okay.
Yeah, so you can actually bring it in gently if you want to. And the clutch rate doesn't mention there, does it? The clutch rate is actually it's a rate of change of ratio. So if I have a clutch rate of 0.5 and I go to a ratio of 1:1, it will take 2 seconds to get there because it's changing 0.5 per second. Yeah. So if I want to go faster, if I put a clutch rate of 2 and the ratio is 1:1, it will take half a second. So it's rate of change per second. This is the example that is in the project that's on the notes. But what I'd rather do is if you just open up Motion Perfect and open up the terminal and have your axes enabled, so you can make sure the watchdog's on and the servo's on in an axis that works. This is for Hoy, axis 1 in your case.
Yeah.
So have the drives enabled, have the servo on, so that it's ready to go. And then in the terminal, just type whatever base it's on. So it could be base 0 for everyone except Hoy, but base 1 for him. And do connect 1,2. And then you should be able to turn the little hand wheel on the front of the case and actually see the axis following it.